covered a couple of relatively disjoint topics. We had a rough definition of what it means to be a conformal field theory or a quantum field theory. We discussed briefly classical field theory. And we discussed what the conformal group is. So now there will be another section which will be algebraic. And sort of also relatively disjoint from the other ones. So here we will study representations of the Virasoro algebra, which, as you will see, is the central extension of the width algebra. And representations. Remember that in two-dimensional conformal field theory, which will be the thing on which we will focus, we studied this width algebra, which was like a conformal killing vectors on the punctured complex plane, and we satisfied some nice commutational relations, which look like this. And then we said that actually for quantum field theory we want things to be represented projectively in general, but we can trade this off for a linear representation if we pass to a universal cover, or to a central extension. So here there is a theorem which says that there is in fact a unique central. This was width algebra. There is a theorem which says that there is a unique width algebra. There is a unique central extension of the width algebra. This is the so-called Virasoro algebra. Width algebra. Okay, right. So maybe before we studied representations of groups, but now we will be doing the infinitesimal version. So we will be working with these algebras instead, which are like the infinitesimal counterpart. Okay, so the width algebra admits a unique, non-trivial central extension. Which is called the Virasoro algebra. I will denote it Vir. So how does this work? This is a span. This is so there is a basis. I will call the basis also with L's, but now capital L's. So let me say that it's so the basis elements are Ln, where n is in Z, just like these ones. And on top of that I will add one generator, which I will call C hat. Okay, so this is the basis. And maybe you remember that we discussed that this is in fact a complex Lie algebra, although you can see that the coefficients, this would make sense also over reals or rational or whatever, but we will see it as a complex Lie algebra. So this is also complex. So it was just complex. Okay, so it's just a complex Lie algebra which as a vector space has this basis. And how does the bracket work? So first of all, this extra element is central, so it means that it commutes with every other element. Okay, I will write it like this. So it just commutes with everything. But more importantly, we will get a modification of this thing above. So this is the main. And now we have 12. Oh no, I missed it. Oh, okay. It's fine. Okay, maybe I should be using. Okay, this is N and this is M. Is that they're different letters? This one here is N. I have it the other way around in my notes. Okay, so the way the commutator works is that it works like the commutator in the width algebra, but then if I commute two things and so this is the Kronecker symbol. This says that this just says that this is 1 if n plus m is 0 and otherwise it's 0. Okay, so this thing essentially says that if I commute two generators, if I take like the algebra operation here is such that I get a linear combination. I get this L with some prefactor. I also get this extra generator C, which is central, hence the name central extension, with some kind of coefficient which depends on n. There is a 12, which is completely irrelevant. You can redefine what C is, but conventionally it's there. But this term only appears if I commute two things such that the sum of the arguments is 0. Okay. Make sense? Okay, and the central extension, remember that we discussed it on the level of groups, but it really means that whatever. So yeah, it's really the original algebra plus one extra generator which commutes. But the reason it's there is because the bracket now gets modified. So it's not the harmless thing. It really brings in something extra, namely, this term. Okay. So now we will be interested in studying the representations of this. So because we want to represent it in our Hilbert space. And so there is a particularly nice class of representations, which is the ones on which we will focus. Which are the ones on which we will focus. So, okay, and this is you might have seen it in various angles, or maybe in different contexts. So let me give you two different descriptions of the same object, of the so-called Verma module. Okay, so first, denote Vir plus. We'll take a subalgebra of Virasoro, which is given by half of the generators. The subalgebra and by Ln, but now only the positive ones. Actually N0, and actually also C and C hat. Okay, and now we will take a one-dimensional representation here. So let's R, H, C, H, be the one-dimensional representation of Virasoro plus, given by the following, such that ln's with positive n's act trivially, so they kill the vector space. I mean, they act by 0 trivially, and L0 acts by multiplication by h. Okay, so this is kind of a slick or quick way to define this representation. After that, I will give you a second, more like hands-on definition. And C hat x by multiplication by C. So these representations, they depend on two parameters, h and c. Let's say hc are real. And I've defined this kind of silly representation where everything that has positive argument, it acts by 0, and these L0 and C hat, they act by multiplication by some numbers. And then we define the so-called Verma module. B to be B. Okay, maybe this. Okay, if this sounds too abstract to you, then I will give you another definition in a second. Equivalent. So we take so U here is the universal element-looping algebra. I'm not sure if everyone knows what it is, but for those of you who know, I take a tensor product of this representation. This is a Verma module, so this is a representation of Virasoro, of the full Virasoro. And the way I define it is that I take it as define it to be a tensor product like this over universal plus. Oh, sorry, for plus. Okay. Okay. Maybe this was too abstract, so let me give you a more hands-on definition of this object.
It's an induced model, right?
Sorry?
It's an induced model.
Yes. From R. Yeah. Okay. So let me now give you a more concrete definition, equivalently. This GHC is the infinite dimensional representation of Virasoro, whose basis I can explicitly construct, whose basis is given by, let's say, the formal expressions of the type this. Okay, so far this is just a word, a bunch of letters. Okay, let's say order these things. So, okay, so I will call my basis element like this. For now it's just purely formal, but just a bunch of symbols. Okay, so for instance, I can take like L minus 7 of 0, or I can take like L minus 1, L minus 1, L minus 2 of 0, that would be one example. Or I can take 0, or like this 0 vector. Or actually, sorry, I'm calling it 0 vector, but this is a not 0 vector. It's just this symbol. Okay, so I will have like a word like this, and then I define the action of Virasoro by first saying what it does in this special case, by the action of Vir on 0 is given this being 0, if n is bigger than 0, L0 precisely returns this number h, and C hat returns C. Okay, so this thing specifies, to make a connection, this is how I'm essentially describing this one-dimensional representation R. This is in this language. This more concrete one. This is the space time by this one vector 0. Sorry, one. I read it. Okay, by this vector. And if I have any other elements, then the way I determine the action, is that I use the commutational relations. So, and the action of any Ln on let's give this a name, on any basis element is determined by using the commutational relations, by which I mean this thing here, which let's give it a name as well. It's hard. Using part. Okay. So this is hopefully less abstract, but maybe if it's not concrete enough, then let me give you an example. Okay, so is the space clear? I'm just saying that it's like objects that look like that. Yes, yes.
I have a technical question. Why do you need to use the universal enveloping algebra? Why can't you just use the Virasoro?
Well, the universal with the fact that I am acting with like.
So you want concatenation, and not just you want to act via multiplication as opposed to the adjoint. Is that the idea?
Because then they're not derivations, so you need to be in another space in which you define. They don't define derivations in the algebra.
Let me annoy you in the break. It's probably better.
Yeah, like I'm wondering, like if I would define it like.
You don't have multiplication in Virasoro algebra because it's a Lie algebra.
So you just have the bracket.
Yeah, the bracket. So to put multiple elements one next to each other, you need
Universal. Okay,
Yeah,
yeah.
a structure.
I see it, I see it.
Thanks.
Yeah.
Thanks. Okay, so let me give you an example. So let's suppose that I start with an element, and let's take that element to be this. So yeah, for physicists, this is kind of essentially what's happening is here like this zero is some sort of vacuum, and I'm regarding half of my generators as like creation operators and half of them as annihilation operators, and I'm building stuff out of them. So this is kind of like a maybe familiar procedure. Okay, so suppose that I have an element of my V HC. Let's say this one, and I want to act on it. And let's act on it with maybe like the element L2. And I'm asking like, what is this thing? And now this prescription which follows from either this or this, if you like, is just that I will now try to use the Virasoro commutation relation, so this thing, and I will try to move this thing all the way to the right, and then I will use the fact that ln is annihilated, sorry, by this zero, this guy is annihilated by all positive ln's. So I will just move it around until it lands on the right, where it will kill this thing. And then I'm finished, and then I will see that the thing I obtained along the way will be a linear combination of expressions of this type. Okay. So let's see. What do I do here? There is the parenthesis. So what I will do here is that I will try to commute this thing around. So I will use this heart relations, which say that each time I flip the things, then I can replace them on the right hand side by this. So this is like this. So here is what I'm using. Okay, I'm just using the commutator. Definition of the commutator, and then here I use the fact that this is, according to this prescription, this is 2 and this is -1, so I have 2 minus -1 is 3 times L1, and this last term doesn't contribute because 2 plus -1 is 1, which is different from 0. Okay, so I can replace these first two guys by this. Okay, let's write it here. -1, L2, -2, 0, +3, L1, -2, 0. Okay, is the algorithm clear? Sorry if it's a bit boring, but there is numbers here, so it's kind of exciting. Okay, so now I will try to move these things here. So if I have a commutator of L2 and L minus 2, then what do I get? I get this, which is 4 times L0. So now I will excitingly also get this term. So if I take 2 plus -2 is 0, so this thing contributes, and I have this C head over 12 times, and now I need to substitute 2. So it's 8 minus 2 is 6. This is C head over 12 times this. Okay, and I need to do a similar thing here, so sorry for this. Put it down here. I need to also move this 1 past the other one. So this is, I'm taking a commutator of L1 and L minus 2, which gives me, this is 1, this is minus 2, that's 3, times L minus 1, and this last term doesn't contribute again. Okay, so now I can collect. And, okay, so what will I have? So, okay, if I imagine that I substitute it for these two guys, this thing here. So first of all, I will have this term, and which L2 is killing this vector. This thing doesn't contribute. L0 acts by multiplication by h. So this I can replace by h. And C hat acts by multiplication by C. And yeah, and this one also drops in the other term because now I have L1 acting on this vector. So what do I get? I get L minus 1, and here I have 4h, and here I have this is 8, 6, 1/2, so this is C half on 0, and from the other term I get 9 L minus 1 on 0. Since this is just a number, I can take it out, and the final result is that I have 4h plus C2, C half plus 9 times L minus 1 on 0. Okay, so we see that like this, using this prescription, you just move the stuff around until at the end you end up with a linear combination of vectors of this form. In this case, unfortunately, because it was so simple, there was just one vector, but in general you could have like linear combinations of many things. So now we get a linear combination of what we have this one vector multiplied by some number. Okay? Does it make sense? Okay. Where's the This will be the class of representations we will be interested in. Oh yes, please.
So is this algebra semi-simple?
So this is infinite dimensional. So let's see. I mean, it should be so. Okay, so it's infinite dimensional, and in infinite dimensional people don't usually talk about. Well, okay, that's also not true. It is somewhat not very far from, or maybe.
Don't we have C?
Sorry.
I mean, don't we have the ideal generated by C?
Fair enough. Yes. Okay. So yeah, it does. It does have that ideal. Okay. So strictly, okay, just because of the presence of C, it's not like the Witt algebra. I guess maybe you can say is. Yeah, this doesn't have. Yeah, I think maybe this one is, and this one isn't because of this extra C that's there. But it's kind of, it has some relation to, or, so a common way to, so there is an analog of infinite dimensional, some of Lie algebras in infinite dimensional, which are kind of good analogs of simple or semi-simple Lie algebras, and the way you work with them is also usually that you add like one generator, like this. So that's why I was a bit hesitating, but okay. So yeah, but strictly speaking, no. Yes?
So if you work at just the base level without the central extension,
Mm-hmm.
is there an easy way to see what an element might look like that does Is there an easy way to see an element that looks like it transforms projectively? Like,
You mean in the Verma module?
yeah, no, just like a yeah. Like, is there an easy construction of some particular element that transforms projectively?
I mean, you don't think about it, but in principle, I guess this whole Verma module should now be just a projective representation. So we would have to account for the fact that yeah, this whole thing, like this prescription for how these things work, it would still define a like if you would so this prescription defines a map which assigns to any such thing an endomorphism of an operator on this Verma module, and the claim is that if you then quotient the Verma module by non-zero complex numbers, then this map from Virasoro to this thing would then be a representation of the width algebra. That's how it should go by this general lore. Yeah, sorry. Yeah, okay. I don't have a.
No.
Sorry, I don't have a
easy
good
question on the
view of
fly.
that.
Yeah. But okay, so then, is the set of phases unrestricted? I guess because it's a central extension.
So, I think what would happen would be. So what would happen, I think, would be that the prescription would still be the same. Like even if this would be with algebra, and this would be now like small l, acting on this representation, then I would say that the result is still the same. But the point is that you are now supposed to regard it as like a module of the prefactor somehow.
Yeah.
Yeah. I mean, these projective representations are weird.
Yeah.
Yeah. Sorry, I can't. I've never seen anyone do that, so.
Yeah.
But it's a fair question. How that works. Okay, so now we have some sort of general prescription. For each H and C, we have this representation space, and there is a. And we know how Virasoro acts on it.
We can see your H in R.
Sorry?
We can see your H in R, because I thought earlier it said H in R.
No, sorry, I meant H and C, like the
No.
pair of two numbers.
It's out and not in. Gotcha.
Yeah, so we now have this space. Yeah, I mean, in general, people study them in complex plane, both of them. You can do that. That's kind of also people do it these days. Okay, so we have this representation. Oh yeah, maybe I should mention some dictionary. So in CFTD, our Hilbert space, on which Virasoro algebra will now act, it will decompose into representations of this. Enough. This will be like a bunch of these things added together. Let me just mention some names. How do people call these things? So C is called the central charge. Hence the name C, I guess. This element, that 0 in these brackets, is called the primary state. So all the other vectors in this, I erased it. Okay, remember that this hashtag was L. This is elements. So all of the other ones and their combinations, the linear combinations, are called descendants. Because we can reach them by starting with the primary state and applying some of these descendants, some of these L's, and the eigenvalues of L0 are called conformal weights. For instance, the conformal weight of the primary state is what?
H.
Weight of 0 of the primary state is H. And last thing, so conformal dimension minus H. So because these conformal dimensions, they make sense for any of these things. Each of these states will have some conformal dimension. And if I take the corresponding conformal dimension and subtract H, and this is called the level. So for instance, let's say I have a So let's say that I have a state which looks like, I have a vector which looks like this. It's another one out from that bunch. And now let's calculate what is the eigenvalue of L0. Again, just using this commutation relation. Okay, so how do I do it? Just as before, I try to commute this L0 all the way to the right, and because then I know how L0 acts on 0, it acts by multiplication by H. So I just do the same procedure. So I flip these two guys, and I get plus 3 of L minus 3. And the last term doesn't contribute. Okay, so I get L minus 3, L0, L minus 7 on 0, plus 3, L minus 3, L minus 7 in the primary state. And I do the same thing in here. So I flip those two guys. And then I remember that the L0 acts by multiplication by H. This is just, I can replace it by multiplying by H. So the moral, so the moral here is that I get 3 plus 7 plus H on my original thing. Okay, so I did this example in terms of, instead of a general statement, but you see that if I act with L0 on any members of the thing above, then what I get is that I get the sum of all those arguments plus the conformal weight of the primary state. So level of this guy is 10. Okay, so since this example was sufficiently generic, you will probably believe me that in general, if I calculate the level of any element that looks like this, then it will be just the sum of all these n's. This leads to the following picture. So, as vector space, we have the decomposition. We can write the whole Verma module as a direct sum in the levels. Okay, so these are this is the subspace of level L. So the lowest level is given by the primary state itself, which has the level 0, and then each time I apply any number of these L's, I increase the level. So I can draw this pyramid, which is what people always draw here. So level 0. At level 0 I have one element in my one-dimensional subspace, which is given by this guy. If I go to level 1, then there is precisely one element, which is given by this thing. There is no other ways to create a level 1 element. Then I can do level 2, and now I have suddenly two options. I can do either this, or I can do L minus 1, L minus 1, which is writing as L minus 1 squared. Okay. How many things I have at level 3? Or what things do I have at level 3?
You have 3 different options.
Okay.
L minus 3,
Mm-hmm.
L minus 2, L minus 1. Slash, it's commutative, but it's the same thing.
Yeah.
And then 3 actions of L minus 1.
Yeah, very good, thanks. And it will be some sort of pyramid, not really a linear pyramid, I guess, but some sort of pyramid.
All the partitions of an integer.
Sorry?
All the partitions of the integer.
Yes, yeah, exactly. Which, let me, yeah, if you haven't seen that before, you can try this as an exercise. That, if you look at the dimensions of all these individual lines, and you assemble them into a like formal function with some parameter that counts these things. Q. This is. So if you assemble all these dimensions of individual lines as coefficients of some auxiliary function, kind of expansion, partition function if you want, you can actually, there is a nice formula for this whole function which is given by this infinite product. Okay, so you can try to prove this if you like, if you haven't seen it before. Okay, any questions? Okay.
Could you just say a bit more about the equivalence of the 2 definitions of the Vira module?
Yeah, fair enough. Yeah, sorry, I was kind of too quick about that. So, let's see. So this thing here, this is the span of this primary state. So this is okay. So now so yes. So yes. Okay. So probably I should have said that these numbers about this. So first of all, what are these objects? Like there is this object. So both this object and this object. Okay. First U. U is stands for universal enveloping algebra, which is the thing that if you have a Lie algebra, you can form a universal enveloping algebra by simply having like words in the generators modulo some commutation relation. So first fact is that both this guy and this guy are representations over of this thing. This on this side is because if there is a representation of Virasoro plus, then I have a representation of the universal enveloping algebra. On the other side, it's because Virasoro plus is subset of obviously subalgebra of Virasoro, so it acts on it, and hence the corresponding thing on the level of U's. And then it's a fact that if you have what's the general fact here? Like if I have a tensor product like this, then then this thing carries an action of U Vir. Simply by acting on the first thing. Yeah. And so this thing is a representation of U Vir. Such thing is the same as a representation of Vir. So far I didn't clarify probably anything. I just tried to remember what those things mean. So now the algorithm from before. So the algorithm from before. So this fact that I can do this kind of, I can use these tricks and I can pass with the commutator to the pass to the right. That essentially says that I'm using the relations in this thing. And the fact that each time I get something like L, let's say 3 and 0, and I say that this is 0, this uses the fact that these L's with positive things, they are precisely the members of Virasoro plus. And the tensor product over that means that I am free to move them from the left to the right. That's how the tensor product works. So if I each time I have an element of Vir plus in here, because from the definition I can move it to the right, and here I know that it kills the thing. Because that's how this representation was defined. And yeah, it should really just be this.
Yeah, no, yeah, that helped. Thank you.
Does that help? Did it help?
Yeah.
Is this generally reducible?
No, that's our next. Yeah, that's where we are going. Very good. Yes. So So before going there, let's define an inner product on this thing, or let's try to define an inner product. Where did this go? Fell down and it's not there. Okay. Okay, so we will now equip with this space with the Hermitian form. So we define a Hermitian form. By Hermitian here, I really mean Hermitian. So I don't mean it. So not necessarily positive definite. Nor actually non-degenerate. Okay, so it can be very bad. Okay. And I will define this on the Berman module. And I will define this again in a sneaky way by requiring two properties. First of all, that the inner product of the primary state with itself, which well, according to our bracket notation, I should have written it like this, or maybe properly speaking, it should be denoted like this. It's a product of these two things, but no one writes it like that, everyone writes like this. Okay, so this is the inner product. Zero with itself. So I normalize it to be 1. And then I require that if I take my generator ln and I take its conjugate, its Hermitian conjugate, it recovers the L minus n for all n. Okay, so by these two conditions, I am claiming that this thing determines a Hermitian.
The action of view on both sides, right?
Sorry?
The second relation you mean inside the action of view? Or are you saying them equal generally?
Equal generally.
Okay.
Yeah, yeah. Okay, so now the claim is that this actually fixes it uniquely. So there's this. Okay, so note that this determines it uniquely. So for instance, let's again example. Let me show you in a calculation how this works and why can I actually extract the number in a unique way. So let's say that I want to calculate the norm of some vector. Okay, if I know how to calculate norm, I know how to calculate any scalar product. So let's say I want to calculate norm of, let's say, L minus 2. Okay, so, well, okay, so I'm not sure how fast, okay, well, let me for now assume that people are already familiar with this, how the bracket notation works, but if not, then let me give you an explanation. Okay, so, I guess okay. So what I mean by this, so if I temporarily give the inner product a name with like round brackets, and what I'm saying here is that I have, this is like probably the ugliest way to write it, like a scalar product of this thing with itself. Now I can use the fact that I can pass with things from one side to the other one for the price of conjugating them. So I can minus 2. Okay, here I use the adjoint. And this thing on the top was simply the definition of this thing. Okay, remember the definition that we have phi a chi for some operator a, then this is the inner product of phi I k chi. Okay. Okay, so now I will apply this property that we demand. So like I'm saying that if I fix those properties, then I can calculate this thing. And so one of the properties says that this I can replace by L2. Okay, now I just need to calculate this. And I will use the only thing I can, and that's the commutation relations. So again, I can commute these two things in the middle. And I end up with L minus 2 L2 plus 4 times L0. But now, again, I will obtain a contribution from the thing at the end, which is, we did it before, so this was C hat over 2. Okay, and now I can remember again that now I'm acting on this primary state, so the first term doesn't contribute because L2 kills this thing. This thing I can replace by multiplication by H, and this thing is multiplication by C. So, voila, the result says that this is 4H plus C half times the scalar product of the primary state with itself, which is 1. That's the property here. So, okay, so in this way I can calculate, again, in this algorithmic funny way, product of anything with anything. Okay, yeah, maybe note. Okay. Any questions?
Does this inner product makes it into a Hilbert space now?
No, because it doesn't have to be positive definite.
Oh yeah, okay.
Or it could be 0. I mean, it probably can't be 0 because I demanded that the inner product of 0 with itself is 0, but it could be degenerate. So, okay, while I erase, I can tell you that for generic values of H and C, this thing is actually well, okay, let me not make any claims. Yeah, but for generic values, it won't have anything terribly interesting happening in it. Like it will be, I think it will be, the inner product will be non-degenerate. And there is like a... But how, with what kind of... So you would need to have a inner product there on the algebra, which I guess maybe you... Yeah, I'm sorry, I'm not sure. It's not usually what I think about.
Sorry for interrupting.
Sorry?
Sorry for interrupting.
No. No. I'm sure that I don't really have a good answer. Maybe if anyone has an insight.
The universal enveloping algebra is the Valach space.
In general, or of this specific one?
Like, yeah, you asked why whether it's a Hilbert space.
The Hilbert space question was about like
The
these
remote
modules.
Yeah, this thing already has an inner product. I mean, this is an inner product, or like something that wants to be an inner product. So I illustrated it here on norm, but there is an inner product actually behind it. Sorry, this didn't answer anything. Okay. Okay, good. So I will also make a note that also follows from this, that each time I see something like this, and this is 0 for all n positive. No, actually for all n negative. So this is the covector corresponding to L minus n on 0, and if n is negative, then it kills it. Okay, just each time you see something like this, you can set it to 0. Okay, now let me leave this thing as an exercise. It really just uses the same tools that we've seen. So if I have two levels which are different, then the corresponding subspaces are orthogonal to each other. So actually, with respect to this Hermitian form. So in fact, the inner product respects the pyramid, like the different layers are orthogonal to each other. Okay. Okay, now definition. So if we pick any vector, I'll call it V in the Verma module. The vector is called singular. If it is annihilated, if it is killed by all positive L's, and it has a level bigger than 0. The level of V is bigger than 0. Okay, so well, if I wouldn't include the last condition, then for instance the primary state has this property. I mean, primary state very famously, if it's annihilated by all the positive L's. Well, it could be that there is other vectors that are also annihilated by it. And the reason it's called singular because is that, well, if such a vector actually exists in the Verma module, then some funny things are happening. Maybe it could be called a funny vector. So each time we have a singular vector, so any singular vector actually creates a subrepresentation. Any singular vector generates proper subrepresentation. Generate really means that I can just take that vector and I just act on it repeatedly with my Virasoro. And the space that I will get will be proper, which means that it's smaller than the pyramid. It won't be the entire pyramid. Call it this S with a superscript V. Okay. But the important property here is that this thing will be orthogonal to the entire Verma module. Okay. So each time I have such a vector, then I will have a huge space, subspace of this module, which is actually on which the metric is actually very, very degenerate. It's 0 on the entire, and not just that, it's also everything in here will be orthogonal to everything in here. With respect to this kind of would-be Hermitian inner product.
Is this one like one-dimensional subrepresentation then?
No, it will be infinite.
But how do you generate it then? Because it's like one. It's not the span of this vector, right?
It's only annihilated by the positive ones. So just as you generate the pyramid by acting with the negative things, so you do it in here. So the picture is actually this is the original Verma module. Each time you have these vectors, it will create something that goes like this, and this thing will be bad. And that is typically also, if there is one, then quite often there is also other ones, so there will be quite a complicated structure of this thing. Different sub-representations. Okay, so let me sketch the proof. Well, so for one thing, okay, so one basis, this thing is given by, well, just as before, because I'm generating it by acting with the Virasoro, I can, similarly to how we constructed the Verma module, I can say that it's like, if I have things like this, they form a basis of my, of this sub, sorry, not on 0, on V. Okay. So the sub-representation means that I apply repeatedly my Virasoro algebra. Each time I get something positive, and well, I kill this thing, so I can actually, it's easy to see that I can actually have things like these that are generating the sub-representation. And the point here is that if you remember how the level worked, then level is additive. So if I have like the level, if this thing was also, if V was itself a bunch of L's, then by acting with further of these guys, I will just increase the level further. This is the picture. I will just go down, 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 which means that the zero vector is not the primary state is not in here. So here. So level of each such thing is strictly bigger than 0, which means that 0 is the primary state, the one I repeatedly keep calling 0, is not a sub-representation. So by this I just proved this proper is smaller. It's not the entire pyramid. But if you're already persuaded by the picture of the pyramid, then you don't even need to. Okay, and to show the orthogonality, so what I will do, I will take one of these basis elements in this subrepresentation. I will take a general basis element from my Valach module, and I will just show that they have a 0 pairing. So essentially, what I need to show sorry, there's a minus here. So if I can show that this is 0, then I'm done. Okay, so remember what this is. This is really like these things. Okay. So here all of the n's and all of the m's are positive. Okay, so this thing here, this is the inner product of this guy and this guy. Okay, so I took a general. I took one of my basis elements from the Valach module, I took one of my basis elements from the sub-representation, and the inner product I can write it like this, okay? By default, by the rules that we've seen before. Okay, and now I don't want to write anything, so I'll just work with my hands. So behold, this miracle that so there is this else which have positive arguments. So let me call them positive L. Yes. Those are the negative ones. So now I want to show that this vanishes for all such configurations. So the algorithm to show that it vanishes is I will use like induction on the number of L's. So what I can do is I pick this guy. This is positive, and there is a bunch of negative L's here. So now what I do is that I will now use the commutation relations to move it all the way to the right, where I know it will kill this thing. So along moving this, like, you know, imagine how it travels around. Each time, by each flip, I will generate some new L, and maybe this kind of number, or like this operator C hat, which is really a number here. Yes. So in this way, I can always I either reach the thing at the end and I kill it, or I can generate a term which has one L less. Okay. So by repeating this, I can go down, 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 until potentially I run out of the L's which are positive. What happens in that case? Okay, so this I can, okay, reduces to, I mean, quotation marks. Okay, I'm thinking how the argument works. So some other letter, P maybe. Q. Okay. So I can reduce this thing all the way down. So by calculating what this thing is, this is equal to a linear combination of a huge number of terms, but all of them they will have a lower number of L's. So I can keep doing this until I end up with a bunch of things like this. But these things are zero by that property. First property up there. So this thing, they are zero unless. What's the unless case?
Precisely.
P1 is negative?
Sorry?
P1 is negative?
No, no. Sorry. By this I meant that. Yeah. I mean, okay. Yeah. All of these PIs are. I assume them to be positive, so I didn't say that. But the only case in which I can't use that argument is if there is actually no L in here. So actually the only case that remains is the case when I have nothing inside, I have just this. But this one I know is zero because
different levels.
Because they have different levels, and the exercise says that they're 0. Linear program is 0. Okay. Okay. So sorry, this was a bit fast. I mean, it's not a terribly exciting proof. It's just you kind of do it recursively or inductively. Or recursively, I guess. You just lower it down, down, down until you end up with this, which is 0. Okay. Yes?
So can we consider that this state V is a descendant of the primary O, but it's also itself a primary operator? Or?
It's not a descendant.
It is a descendant. It's descendant just because it's not on the tip of the pyramid. Everything below is called descendants.
Okay. It's not an image of the any. Can you create it by acting on 0 with ln's? No, right?
Yeah, yeah. I mean, everything in here is created by accident. Yeah, that was the construction. It's like the basis elements look like this with 0 here. Okay, so let's see. Right. So this thing below it is a sub-representation. That's truth. Okay. Is it of the same form? I guess. Yeah. I guess I can somehow implicitly use that fact by saying that there is a basis which. Yeah. Like when I said that it has a basis like this, I guess that kind of shows that it's. Yeah. That it will be a different Verma module. Yeah, yeah. That seems to be what's happening. Yeah. Okay. So all of these subpyramids are themselves like pyramids. Yes. Good point. Was that your question? Yeah. Okay. Good. No. Okay.
The highest weight representation.
Yeah, this is exactly the highest weight representation, or maybe in this case maybe the lowest weight, because it's, if the weight is kind of the the level or something, then it's generated by the thing on the top, which has the smallest level. So I guess this is the lowest weight. But yes, exactly. Very good.
Can you find out if you have a singular vector based on H and C?
Yes. And we will get to that very soon. Maybe now? No, there is a couple sentences before that.
Okay.
Well, the result will be unsatisfactory because I will give you like one-way implication, but then I will state a theorem which actually says when this happens. But maybe in the meantime I can say that so you saw before how one calculates. So imagine that I want to calculate such things. Then we had an algorithm before where we were applying, this was itself a linear combination of some else acting on the primary state. So if I act with something like this, then I have an algorithm and I know what happens if I just move it around. And the result is in general horrible, but it will be some function depending on H and C. And that function probably is polynomial even H and C. So if you want that you have a vector where all such things vanish, then it's essentially vanishing of some infinite number of polynomials. H and C. Like yeah. Wait. Wait. That didn't make complete sense what I said, but no, because you don't know what level this V will be.
There will be an infinite number of polynomials, maybe of the same degree, because each degree is given by the level. The degree might be given by the level because you need to do level number of commutations. Or actually no, because you can have different number of things.
Yeah, the thing where I was going with this polynomiality was they want to say like if you just pick randomly some like linear combination of these basis vectors with some like very weird like no wait sorry. Suppose that these numbers H and C would be like transcendental.
Okay.
Then I think that there will be no singular vectors.
There will be no.
No, it doesn't really show that, right? No singular vectors. Yeah, like, generically there is no singular vector. That's like a secret that I'm going to say. I wanted to argue some sort of polynomiality, like the fact that. Okay, no, no, I didn't say anything, but I thought there is like an easy glimpse about why generically they are irreducible, but I don't see it now. So.
I mean, polynomials have finite number of solutions, so maybe they are countable points and somehow use them.
But I also don't know like. Well, okay, yeah.
Anyway.
Yeah. Sorry, just tangled myself. Okay, any other questions?
Are there other sub-representations, or these are like all of the only way to construct sub-representations?
That's a pretty good question, and something that I should know. I think there are no others. I think there are no other, because if there would be a vector which would generate a sub-representation, but it would not be annihilated by any of the negative, positive L's, then I could apply positive L, which would bring it higher up, and it would
generate everything.
Yeah. So I think you can argue by contradiction there. Okay, so maybe there was some subtlety that I missed, but I don't think there is any others.
I have a question about the structure of the module.
Uh-huh.
Okay, given an element of the module, can I always find like a level? Is this?
Sorry, say again?
Given like an element of the module, can I always find like a level? Sorry, an element of the module, does it always have like a level, or are there things which just don't?
Yes, very good. I was yes. No, of course you can take a linear combination of things with two different levels. So yeah, actually the way it's written in my notes, I decided to skip like part of the definition of a singular vector was that it's annihilated by all these positive L's. And the level is bigger than 0, and that by that in a subtle way I imply that the level of that thing is actually defined. But if it's not, then I think you can probably just decompose it into things and but yeah.
Can I say that it lives? Sorry, can I decompose it such that there's a maximal level part if I write it as a linear combination?
I think so. That makes sense to me. Yeah, if you would have like something which would be singular, but it would not have a well-defined level, then you can probably take the highest. Yeah, I think you can do that, and that by itself would be singular. I think.
I think this module can't be a Hilbert space then with the inner product you give, because if you take the linear combination of sort of each level, that forms a probably nowhere dense subspace. So then you can take a union of these to write the entire space, right? And so by bare category theorem, you just can't be a Hilbert space.
Mm-hmm.
Nice.
Okay, good. Thank you. Thanks, very good. Okay, so the corollary now of this statement is that the new representation, so I can mode out, I can quotient out this thing, this sub-representation, and I have a new representation. But the important here is that this thing inherits the Hermitian form descends to it. Inherits a well-defined, precisely because I am modding out by something that's orthogonal to everything. Well-defined Hermitian form. It could still be degenerate, but at least it's well-defined. Okay, so I can just remove this zero norm state. This okay, I used the word I haven't used before. I can remove these bad guys and I get something that's still has a Hermitian form. Okay, now let me summarize the next thing by proposition, and I won't prove this. So if I now do this for all singular vectors in my entire Verma module, so I mod out the corresponding sub-representations, then the thing I get is actually irreducible. By quotienting out this SV for all B. So all singular vectors. You obtain an irreducible representation of the Rasoro. And I will denote it by I, H, C. And these are the representations that we will be interested in. These are the things that form, out of which we, in general CFT, you can assemble the Hilbert space using these things. And okay, here a note that I somehow felt before was natural, well, okay, let me just take this as a fact. Note that for generic values, of HC, there are no singular vectors. And hence, the Verma module is isomorphic to this IHC. Okay. Generic means that if you would take like a dart and you would throw it at the possible range of the values, then you would always hit a place where there is no singular vectors. There might be isolated points which behave differently. Okay, and maybe one more definition. So these resulting guys. So now we have a way to construct the Virasoro representation for any H and any C. I just take the Verma module and I quotient by all these singular, all the submodules generated by singular vectors, and I get a representation. And I will call this unitary. It's called unitary. If this induced Hermitian form that I have on it is positive definite. Okay, and one noting thing. So note that if the original Verma module contained a vector with negative norm, who had a negative pairing with itself, then for sure the induced I can't be unitary. So if this thing contains a vector of negative norm, okay, you know what I mean by norm. I mean the Hermitian pairing of the vector with itself. I mean, norms by definition they should probably not be negative, but here I really mean the pairing with itself via this potentially bad killing form, Hermitian form. Okay, so if there is a vector of negative norm, so-called ghost, although there is other versions of ghost in physics, then this IHC is not unitary. Okay, so at least we have a nice criterion for testing when these things are not unitary. We can just look at the original Verma module, this horrible infinite dimensional monster, and we can just see if there is at least one vector of negative norm. Okay, and now the theorem. Okay, proposition. So there is an easy way how to go one way. Proposition. So unitary requires that both H and C are positive. Okay, so unitary implies H is equal to 0 and C is bigger or equal to 0. Okay, if I have any other values, if either of them is negative, then the module is not unitary. This essentially says that if I have this range, this real range of these parameters, then the only possible unitary things are here in the first quadrant. Okay, and the fun. Okay, this is a fun proof. So let's calculate the norm of this one particular state, which is primary state acted upon by L minus n. And let's say it's strictly bigger than 0. Okay, so now we are sitting in a particular Verma module. Okay, we fixed H, we fixed C, and let's calculate what this is. So what is this? This is using the fact that those two things are adjoints. I can write it like this. And here I can again use the only trick that I have at my disposition. I can combine those things around. So I get Ln, L minus n, Ln, which contributes trivially because Ln kills 0. Then I have plus 2n, L0. And then I also have this thing with the central charge, n cubed minus n. Okay, so I can write immediately that this result is given by 2nh, because L0 by h, and C hat I multiplication by C. So C over 12 times some number. This number multiplies now the product of 0 with primary state, which is 1. Okay, so the result, the final result is that this is 2nh plus C over 12 and cube minus n. Okay, so now what can I guess from this? So if the representation in the end, if I have any hope of having a unitary representation, then all such elements need to have non-negative norm for all n. So for instance, what happens if I set n equals to 1? In that case, the second term vanishes, and the first term becomes 2h. This should be non-negative. So this is how I show that h has to be non-negative. Okay, so if n is 1, then this implies that the positivity of this implies that h has to be non-negative. What about c? So I use the special value of n equals 1 to determine that h has to be non-negative. Now I can do kind of the opposite thing. I can go to infinity with n. So suppose that if C would be negative, even if very small but negative, then with large enough n, this term would be bigger in absolute value than this one, so the whole thing would be negative. Okay, so the limit n goes to infinity shows that C has to be non-zero, non-negative. Because if it was negative, then with large enough n, this term would dominate the other term, and it would be negative, which is bad. Okay, perfect. And okay, I guess we can finish it with this theorem, and then we can have a break. So this theorem I will not prove. And this theorem is due to Friedan, Schenker, Goddard, Kent, and Olive.
GKO.
The famous FQSGKO theorem, I guess.
It's a real reference, right?
Sorry?
It's a real reference.
I think so, yeah. And so the statement is that this thing is unitary if and only if either of the two happens. Either C is bigger or equal to 1, yes, and H is bigger or equal to 0. So in the picture, let me draw the picture. In the picture, bigger. H, this is C. Each point here represents a Verma module. Now what was shown there is that everything in here is good and gives a unitary representation. But the other option is a discrete. There is a discrete number of other choices, and that's where is it? Here it is. This is the case when the central charge takes the particular value, which is this. Note that this is always okay for m being in 2, 3, etc.
Is that a 6 or a sigma?
6.
Thanks.
Yeah. Fair question given my handwriting, but it's 6. Yeah. Yes. So you see that this is always smaller. This is always between. So the smallest thing you can have is the numerator. The denominator is at least 6. So this thing will be always between 1 and 0. So this thing will correspond to some bunch of isolated dots here. But so far this is only C. So what is H? Okay. Okay, and H is equal to this expression. Okay. This is R, and this is S. So you see some new letters of R, and this is S. Squared minus 1 over 4m plus 1 for R, which is in between 1, 2, etc. up to n minus 1, and S, which is 1, 2, up to R.
And the m has to correlate between the two.
Yes. Yes, and it has to correlate. Yeah. So there is. So first part of the sentence is that there is only a discrete number of C's that can actually have something on the top. So there is, if you take 2, then you get 6 over 6. You get 0. If you get 3, then you get 3, 4, 12, 1 half. Really? 3 times 4 is 1. Okay. Yeah. Okay. So then you get something in here, and you will get. And for each values of C, there will be some finite number of possible ages. They are labeled by these 2 finite parameters. So the picture looks like this. That if you take m equals to 2, this thing is 6 over 6, which is 1. So C is 0. And the possible ages, they can go from 1 all the way to 2 minus 1. So there's only 1. S can also only go up to 1 because it goes to R. And if you put R and S equal to 1 and M equals to 2, those two are 1, then you get 3 minus 2, which is 1. 1 squared is 1, so you get 0. So in the first column, there is this point, and then there will be a bunch of points like this. And they will kind of, more of them as you get closer to 1. So yeah, this is the representation structure as far as the highest weight representations of Virasoro go. Okay, any questions?
Which one we care in CFT?
You care about all, well, okay, actually the unitarity, okay. So physicists are used to unitarity, but in fact there is even like there is even some like physically relevant models which don't require unitarity. So actually there can be stuff beyond this. And even actually for string theory you can argue that because of the time dimension is kind of different for those of you who know what this means. There's like an extra sign. And actually that CFT is also not supposed to be unitary. But that's fine for string theory because you do some other stuff. So unitarity is actually not like that much required. But the cool stuff, and I will get to that after the break, is that these things, it turns out that there is, for each of these values of C, which means a bunch of dots above it, there is a model, there is a well-defined CFT, means that you can put these representations together to form actually a well-defined CFT, and they correspond to what is called minimal models. And one of the big successes of CFT was that people identified that those models actually describe some like real world scenarios. For instance, this is an empty model. The next one when you take m equals to 3, that corresponds to Ising model in 2D. If you take m equals to 4, you get the so-called 3 critical Ising model. Sorry, the critical Ising model. The m equals 4 is the 3 critical Ising model, and m equals 4 is so-called Potts model, and so on and so on. And the fact that people identified them with these things, was a big success because those things are, the next part, like the CFTs are so heavily constrained that you can just use some sort of algebraic or maybe some analytic tools to actually like calculate explicitly all the correlation functions that you care about. And in some sense you can like completely solve the model, like you can answer essentially everything that you ask for by embedding the formalism in this kind of stuff. And for string theory, you kind of, so these are kind of statistical models. And for string theory, I would say that the ones in here are kind of particularly interesting. So there will be one living precisely in one, which we will see as our examples. That's the free boson in bosonic field. Sorry, in bosonic string.
Thank you.
Okay, so should we make a break until 6? Yes. So now follows a slightly, or actually not slightly. It's a massively hand-wavy part. Where I just want to sketch some of the other ideas and essentially tell you things without providing too much supporting evidence. But since we want to finish this in finite time, there is something that I think needs to be mentioned. So let me just mention them here. And this is, I will call this part structure of two-dimensional CFT. To the CFT, and to stress the nature of this, I will call it a fairy tale. Okay, so this is a part which kind of bridges these things that have happened so far, and I will just tell you now some properties that the CFTs always have for some reasons, and I won't go very deep into those reasons. But I want to. The conclusion will be that the CFT is a very heavily constrained object, and it actually is so much that you can just define it by a bunch of numbers. So that's essentially the point. And then, using some other part, which I will tell you about, I will translate the story from the perspective of Hilbert spaces to the perspective of operator product expansions. And then we will arrive into a completely new universe where things are kind of very different and they're kind of fun. So that's what I want to end up with some calculations. Okay, so let me tell you about some features that people do. Features of CFTs or procedures that people do. One of them is the operator product expansion, which was mentioned before. Sorry, no, I don't know. No, that comes later. Operator state correspondence. So, if you ask people about what's important, like what things do CFT, why are CFTs special, then well, this is one of the things that there is a statement that there exists a one-to-one map between fields, which, if you remember, these were some distinguished class of operators. In fact, you can, if you want, you can revert this definition to, revert this statement to a definition. You can say that this is actually what defines those fields. So there is a one-to-one map between fields and states, and vectors in states, and the same as vectors. Vectors in the Hilbert space of the theory, and the correspondence. Let's say on the punctured plane, given by, give me an operator, I will act on this operator at 0. So let's say all that Q. Either way, you don't even need to know about this prescription. There is a claim that there is a one-to-one map between states and operators. And this leads to the following naming convention, that fields corresponding to primary states or descendants are called primary states, primary fields. All primaries, if you want to be primaries. You want to, be more like jovial or descendants. Okay, so just as in the Hilbert space there is the primary state sitting on the top, and there is some descendant that the same gets translated to the structure of the field. Okay, and I will call these primaries, I will call them OI. It's the general field we call O alpha before, so I'll call this with Latin indices. Okay, this is one sort of sketchy property, in the sense that I sketched it, not that it would be sketchy. Although, and the other property is something that I will call a holomorphic, anti-holomorphic separation. So this means that our Hilbert space in a general CFT is the sum of blocks, direct sum of blocks of the form H whole tensor H anti-whole. And one way this is manifested is that, one way that this happens is, okay, one way to say what this means is that there is actually two separate copies of the Virasoro algebra, one acting on here and one acting on here. This is a thing that if you open any paper or book on CFT, that at some paper this happens, at some point this happens, that actually it's a sum of blocks, and those things, each of these, for instance, each of these things, for instance, the holomorphic part, this is a direct sum of these i's for a fixed C. So C is usually fixed for the entire CFT. It's like every CFT has like its own central charge, and we have some subset S in the real line. So we choose these ages to be, like we have one fixed central charge. So in terms of the picture, the CFT always has it like it always works in a way that you are in a fixed central charge, and then you choose some subset of ages that lie over it, and you take their sum. Actually, I'm cheating because sometimes this is actually like a direct integral. So there is like it's like a continuous parameter, but okay, whatever. Okay, so yes, so and the same for the anti-holomorphic. Actually, see it. This can be a different set; doesn't have to be the same one, and it can have a different central charge. Actually, I lied before. So each CFT has two central charges, like left and right, or holomorphic, anti-holomorphic. Often they are the same, but not always. Okay, so C and C prime fixed for entire CFT. Okay, and one nomenclature is that these kind of holomorphic things, this thing you usually call the chiral part of a CFT. Okay, this is probably the most hand-wavy part. So, but yeah, so I'm essentially saying that that each CFT, the Hilbert space of that, you can decompose it into such things, and yeah, and there is a couple of sketchy things that happen. Like for instance, you might object like, why is there two Virasoro algebras if there was just one at the beginning? Like the moral of the story was that we had like conformal algebra and it was supposed to act. Why do I have two of them? And I think the answer to that question is in the fact that this is a remark which maybe no one is interested in, but the Virasoro was a Lie algebra over complex numbers. It was given by these commutation relations which I erased while we were away. It's not here. But it was a complex Lie algebra, but we remember that that was kind of just like an auxiliary thing. It was supposed to be, we were supposed to take it as a real thing anyway. So it's a complex Lie algebra, but we're supposed to treat it as a real Lie algebra. And in fact, the commutation relations for Virasoro algebra, they made sense for any field, maybe of characteristic 0. Like if you looked at, there was divided by 12, so maybe characteristic different from 2 and 3 or something. 4. Okay. Not important. So you can, this Virasoro algebra actually seen as this complex Lie algebra, you can see there's actually like some real Lie algebra tensor with complex numbers. Okay. Now, a second fact is that when these Hilbert spaces are all complex, and in general in physics you have like some real group acting on those things, but often for convenience you trade off your real Lie group for a complex one, because usually, well, these are complex representations, so they always kind of factor through like a complexification of the, let's say, Lie algebra. If you have Lie algebra, a real Lie algebra acting on a complex Hilbert space, then it always factors through the complexification. So we can just as well talk about complex representations, complex Lie algebras, those are simpler. So in the case at hand, you actually need to take your Virasoro here and you need to complexify it. Or not need, but you can. Because you are acting on a complex Hilbert space. And it just so happens that because this thing was already a complexification of something, then doing this thing, you actually end up with 2 copies of Virasoro. Where all these things, well, this is like tensoring over the real numbers. If you complexify something that's already complex, then you end up with 2 copies of that. That's like C tensor. It takes real complex numbers, complexify them. Look at this thing. So, is there anyone who is not confused by this? Okay, good. It makes sense.
So, sorry. So you're saying this is like the reason behind the chiral splitting of a CFT?
No, no. This is the reason why there is 2 Virasoros. I don't want to go that far.
Okay, fine.
Maybe. I didn't want to say that, but I don't know. Yeah, maybe. Yeah, that makes sense. Why not? Yeah.
So why would you try to complexify again if it's already complex?
Because you were supposed to. Because this thing. It was a real Lie algebra. Like it was also complex, but the way this arose was that this is an algebra of real killing vector fields. It just conveniently assembled itself into something complex. But originally it was supposed to be real things, so you should still regard it as real, which you can. So this is a real Lie algebra. It's also complex, but it's real in particular, so you can't complexify it.
Is it like looking at SU2 as a real Lie algebra, which is a complex algebra, but it's also real?
No, SU2 is not a complex algebra. SU2 is just real, but SL2 is SL2C. Oh, yeah, that's one of the subtleties. Like SU2 is only SU is 3-dimensional real Lie algebra, so it's not complex in any sense. But SL2C, yeah.
The origin is complex. It's complex matrices or complex values.
Yes, but that's just the way you construct it. But as an abstract Lie algebra, it's real.
Ah, okay.
But SL2C does have that property. Yeah, people often do that with SL2C. Like that thing, yeah. That thing you can treat as a 6-dimensional real Lie algebra. So that's the kind of analogy that I'm doing. Yeah, as if this would be like SL2C, which is a complexification of SL2R. Yeah, kind of. And then I would complexify it again.
Now it's
Okay, well. Okay, if this remark confuses you, then feel free to correct it. Any questions?
Are these blocks what people call conformal blocks?
No,
That's completely other thing.
that's different. Yeah.
Actually, I do have another question, sorry.
Sorry?
Sorry, I have a question. This fact you wrote, Vir tensor C over the reals being equal to 2 copies. I thought you just said that C and C prime are different.
Oh, I did say that, yes. square well with this, right? Yeah. Well. Yeah, good catch.
Like when you see it in the wild, it's always like vir C tensor with vir C bar. So.
Yes.
But are they necessarily complex conjugates of each other with using this trick?
I think generically they can be different, but then when you actually sit down and think about it consistently, they're like forced to be the same. I'm pretty sure.
C prime be just I times C. Or am I smoking something?
No, so, well, so, I know of instances of conformal field theories where the C and C prime are really different. Like if you do like, I don't know, heterotic string or maybe some Constantigov systems or something. So, yeah. I don't know how to explain this discrepancy.
No, it's okay. Thank you.
It could be that this is the origin, but maybe then at some point it makes sense to somehow start treating them. Yeah, I don't know. Good catch. Yeah. I didn't prepare this, so I don't know.
No, thank you.
I mean, you can still make it work, right? Because the central charge in the Virasoro algebra doesn't have a value. It's only its representation that has a value.
Yes.
So you still have vir plus vir, but you just have a direct sum of two different representations.
But then the C will come from nowhere.
Like the representation of a direct sum doesn't have to be two copies of the same representation. They can be two.
Okay, yeah.
So you can have two values of C.
I see. Okay. Maybe then that just. Maybe that thing says that like representations of if I tensor something with C on reals, then yeah, that's what this thing says. That actually I have more freedom in yeah. No, it's not that the representations of this is the same as the representations of this. It's like twice as much if we believe this equality.
How does this relate to, like normally the argument is kind of, you have LNs being defined as, like in one of them in Z and one of them in Z bar. Sorry, normally the physicsy argument for the reason there's two copies is because you have a Z and a Z bar and you treat them as independent. Like how does this square with this?
Yeah, so in this part of the story I haven't mentioned, and yeah, so the way this works is that like the corresponding operators, they will be like products of holomorphic and anti-holomorphic. Like the operators corresponding to states living in a tensor product of these two things, they will be like tensor product of operators depending on Z and ones depending on Z bar.
Yeah.
I think.
Yeah.
Is that, sorry, is that,
yeah, I just don't really understand how that, like, with this.
you mean like how? You mean like where is this reflected there?
Yeah. Like, is that coming from a similar reasoning, or?
Okay, good question. Okay, I don't know in front of my head. Sorry.
If at the level of the algebra you have a direct sum, then at the level of the group transformation you just have the. It's just a tensor product, no?
Yeah.
So it means that if your thing is tensor Z and Z bar, then you can have two transformation, one holomorphic one and one anti-holomorphic one. And so at the level of algebra, it's just represented by the fact that you get just two copies of the sum.
Yeah. No, I was more going the other way.
Sorry, I don't have a.
That's okay.
I don't have a good answer. Okay, this was supposed to be a sketchy part anyway, so. So then just to pull this up, then well, and it's a third hand wavy part. That data of a CFT. Okay, here I will just write some things. So we said before that the goal of a quantum field theory is to calculate correlation functions. And we said that sometimes you have this nice operator product expansion formula. So if you know how to trade off a product of two operators, well, not you know, but it's sometimes it's possible to trade it off for some other operators, or for just linear operators. So if you have a correlator with like many such insertions, you can sometimes just use this repeatedly until you bring it down to just copies of the correlators with linear operators, and those usually you can evaluate easily in some way, or maybe they're 0 or something. So kind of what I want, where I'm going in the sketchy part is I want to see that kind of knowing this is like essentially knowing everything about that theory. And there is an argument that makes CFTs particularly valuable. It's the structure of this space of operators, which is the same as space of states. That we know that all the descendants can be obtained in the Hilbert space by acting on the primary operators with the Virasoro algebra generators. So this actually translates to the fact that those things, so these things can be completely recovered in a purely algorithmic way, independent of like CFTs or anything, just like there's like a horrible but in principle finite algorithm. So you can recover this by knowing simply the corresponding numbers for the primary operators. So here alpha was like index running over all of the operators, and I'm just saying this by itself is probably not terribly surprising that you can actually, since those operators you can recover them from primary operators in some way, you can also recover those functions from those functions of primary operators, which is less data. Okay, that's where I'm going, less data. Now, it turns out also that when you examine the conformal properties, or like the properties of these both sides, how they behave under conformal transformations, then this thing will tell you that actually this as a function, it has to be something very specific. Namely, it has to be a bunch of numbers and then a fixed so if you know the conformal weights of the operator I, j, and k, then you know that the coefficient function is this, where those things are just a bunch of numbers, constants. So in fact, this conformal symmetry is like so handy, so strong that it leads to the fact that so you can actually recover the whole CFT, entire, or more precisely in this case, chiral part. So from now on, I will focus only on the chiral part. I won't say it. I won't stress it again. But sorry, I will kind of focus only on like the holomorphic part. And we can recover the entire chiral part from the following bunch of numbers. From central charge, this is what we need to specify. We need to say what the primaries are and what their conformal weights are. Conformal weights, hi, and the primary operators. And finally, these structure coefficients, which is just a bunch of numbers. If you're lucky, it can even be a finite bunch of numbers. This is one way. Like it's not true that any such set of data will define a CFT, because a CFT, as you probably by now acquired the feeling for, is like a relatively complicated thing. But in particular, it's determined by this, or at least its chiral part. And so, but it turns out that there is further restriction. So, for instance, if you have an operator product expansion with like maybe 4 or 3 things, then there is various ways how you can use this identity to reduce it down to just correlators of linear functions. And on this sense, it tells you that this needs to give the same result. So there is actually like some other conditions. So those ones I think are called crossing relations, crossing symmetries, maybe, whatever. So there is further conditions that these structure coefficients have to satisfy, sort of like analogy of associativity, kind of. And so it turns out that actually there is further constraint on this algebraic data, and there is even like whole programs of like determining, very successful programs of actually determining possible CFTs by simply trying to solve these constraints, and this is called conformal bootstrap. because essentially you could reduce the stuff up to some bunch of data, then with some conditions, then you can just employ some computers and you can try to, or maybe even some analytical techniques, and you can try to actually determine those. I think actually the constraints are so strong that in principle you can determine the last thing out of the first two. I think sometimes, maybe not always. I don't know. Not all pairs of these are also allowed. Like there is further constraints. Okay. So this is the end of fairy tale. So if this was not satisfactory, then sorry. But okay, let me just make one definition to pretend that what I said up to now was very rigorous. So the CFT with the finite with S finite. So S was this set of these possible primary, the conformal weights of the primary operators. Is called a minimal model. And there is a theorem which says that these minimal models can be classified, especially if you require unitarity. So unitary minimal models are classified, and they correspond. I won't even write this, but they correspond in terms of this picture that we had, where this was C, this was H. Remember, there was like a continuum of possible unitary Verma modules, and then there were some like, there was this one, and there was something like this, and there was something like this, and then something like this. So it turns out that the only possibility to have a finite unitary thing actually corresponds precisely by taking these individual columns here. So the unitary minimal models correspond precisely to these, taking this, or this, or these, or these, or these. So there is a discrete number of them, and if you remember, the central charge for those was like 6m plus 1, 2, 3, blah, blah. And the part of the theorem states that you need to include all of them in the line above.
I'm just going to point like third down there.
Oh, thank you. This is precisely why I kept it, so that I could point at it and then I forget about it. Yeah, thank you. So yeah, it's precisely, you need to take one of those, fixed m, and you need to take all the associated ages. If you leave one out, then it won't work somehow. You need, yeah. And it was, well, and this is something that I alluded to before, like it was a great success of CFT to identify that these green columns, they correspond to interesting statistical models. Like this one, this is the empty theory, so this is nothing empty. But this thing here, this is the Ising model, or critical Ising model. So this is m equals 3. And let's see, so for m equals 3, what can we have? We can have, well, okay, I did a calculation before, so let me just tell you the result. So in this case, C is 3/4, so 1/2. And the possible values above, there is 3 of them. There is 0, there is 1/16, and there is 1/2. There's 3. Yes, and well, the thing I have written down is that this thing, if you come from like solid state physics or statistical physics, then apparently the primary operators corresponding to these ones are the so-called spin operator and the energy density operator. So, yes. I'm not sure if this is how it was originally discovered, but I can presume something like this happened, that people were talking about the critical Ising model, and they were like, oh, there is like this, it has the scaling properties, and there is some interesting operators in the game, and they could kind of deduce that actually in CFT they would have these and these values, and that kind of uniquely identified this model with this thing in here. And the same happened for many other models. Okay. Yes. And maybe final sentence for this part before we go to the last exciting part, is that there is a more general, sometimes it happens that there is many models which have a symmetry which is larger than Virasoro. So for instance, if you know about the West-Zumino-Witten models or some such things, then they have a symmetry which is larger. So there is something bigger than Virasoro. And so this theorem says that if you care about models which have a finite number of things, then there is only these guys. But it could be that you have a CFT which has this larger symmetry and which has finitely many representations of that symmetry. So it could have infinitely many Virasoro modules, but it might have a finite number of these larger symmetries. And such CFTs are called rational, and they are particularly nice in some sense. So there is a generalization of the story, is the point. Yeah?
So if you have seen the regime where you have a continuum of a allowed value for h, do you also have to take all of the primaries into account, or
sorry, do you have?
Do you also have to take all of the primaries into account, or you can also have some consistent CFTs where you have a discrete set of primaries operated, even in the regime where you have this continuum?
Good question. I don't remember. I don't remember. I kind of suspect that maybe you need to have a continuum of things involved, but that's just my suspicion. Probably this is surely well known, but I don't know. But yeah, good question. Okay. So if you didn't like this hand wavy part, then I can understand. This was partly as a bridge to the last section, which is very independent of it. So now we can refocus. The last part is about operator product expansions and the stress energy tensor. And maybe one example. But yeah, in the meantime, any questions? This will take me at least half a minute to raise this. There is also super conformal field theories, which kind of mix this thing with supersymmetry, and there is also something larger. You can also study minimal models for that. It just means that there will be, I think, finite limit bigger things.
I have a question actually.
Yeah.
So we constructed these Verma modules in this specific way. Is this like the only representation that we care about of Virasoro algebra?
As far as I know, yes. I think there's an abstract algebra probably has more representations, but as far as I'm aware, these are the ones that you have in CP. I don't have a good argument why that is. But this is why, this is why I included this in the hand wavy part. It just says that this is what happened in CFT. It's direct some of these things. Maybe there is some sort of argument. Okay, so now comes the last part. Which will be kind of very disjoint from what was happening. And in particular, there won't be any Hilbert spaces. Instead, we will be working purely with some basic complex analysis. So this part is called operator product expansions and energy momentum tensor. And so, if you come from a CFT area, then you would probably be surprised that, well, there is this one object which I haven't talked about yet, and that's the energy momentum tensor, or stress energy tensor, or stress energy momentum tensor. Maybe other names. So it's kind of like it's one of the crucial things in there. So let me just start by this sentence. In every CFT, there is a distinguished operator T called energy momentum tensor. T, I suppose, stands for tensor.
Typically, because it would be the kinetic energy in classical mechanics, which is denoted by T for some old books.
Is that the reason?
Yeah, because if you work in a classical theory, it would be just the kinetic energy.
Okay, so nothing to do with tensor. It's this. Okay, yeah, I can buy that. Okay, cool. So the way this arises is that one way to say it is that it's linked to conformal transformations. I won't say it has I mean, there is an interesting geometry and everything behind it. I won't say it here, but if you're interested, you can look at the lecture notes, which have been also updated a little bit. I fixed some typos. So there is an appendix which discusses how classically this thing arises and all that. But the only thing we will need for now is that we have this tensor, and the link to conformal transformations is that if you go, for instance, to puncture plane, then you can see this thing as being something whose Laurent coefficients n plus 2. The Laurent coefficients of this thing are the Virasor generators. The Virasor generators somehow naturally assemble into this object. But actually, from now on, I will just take it as a fact that there is this interesting operator, which is kind of a thing that encodes the conformal transformations. And from now on, we will forget about operators, or like Hilbert spaces. So from now on, the game kind of will be a bit different. So from now on, we will play with T and primary operators only. So, okay. And so what we will do, we will now work with OPEs. So first claim is that the OPEs that we will be dealing with, they will have the following form. I take two operators, and yeah, this is a pretty general statement. So they will have the following form that remember there were some coefficients functions, but actually the coefficient functions, they almost always become just Laurent polynomials. The thing here is that you see that written it a bit strangely. So you go, this n is some positive number typically. So there will be like infinitely many regular things when this is actually in the numerator. But there will be also a finite number of poles. Well, okay, written in a funny way, but there is like the point is that there is a pole of finite order of order n. Okay, this I will take as my assumption, and then I will introduce a couple of things that are common in the literature. So first of them is that I will, whenever I have two equalities, it's a bit of a funny thing. So this is the, in this notation I will introduce the symbol tilde to mean equality up to regular terms. So this means that, for instance, if this operator product expansion of two operators was like this, then by writing tilde, I can write things like this. That they are actually equal up to regular terms. This means equal up to regular terms. This might sound funny, strange, but yeah, okay. It's again one of the facts of life that the interesting stuff here comes from these poles. Okay, so this was just one point where I introduced the tilde, and now, okay, further facts. You can regard them as like rules of the game that I'm going to play. So remember that we had we now know what it means in principle to be a primary operator. It's an operator that corresponds, by this mysterious operator state correspondence, to a primary state. So there is some distinguished classes, and we know what it means to be primary. It means that it sits on the top of the pyramid. So now there is a claim that in terms of this language, this thing translates into a statement that if you make an operator product expansion with the energy moment tensor, then this thing will look as follows. Okay, so this is always primary of weight. So there is kind of like a purely OPE way to discover when an operator is primary. And it's primary if and only if when you take a product with the stress energy tensor, which, remember, is something that encodes the conformal transformations in some way. Then up to the regular terms, there will be a second order pole where the operator itself appears, multiplied by this number, this weight. And there is the term like this. I apologize since this looks very, if you haven't seen it before, it's probably very, random. And like I could have written 3 here and no one would notice. But yeah, the claim is that this is what the stuff corresponds to, and if you can look into the literature how these things are derived, but I thought that it's maybe more fun to just postulate this and then work with it. Now, the second fact is that if a CFT has central charge, okay, this is again a chiral part, central charge. CFT has central charge C, if and only if, again, there is a statement that the operator product expansion of the stress energy tensor with itself has a 4th order pole okay. So I promise that these are the only 2 random expressions that are like unmotivated things. But yeah, so for those of you who work with CFTs, like you know that there is an argument how you can pass between the operators and between this and the Laurent coefficients. You can do some sort of contour integrations, and then you can discover that this statement that I've written here is precisely equivalent to the commutation relations of the Virasoro algebra. And the fact that there is this weird 4th order term that corresponds to the fact that there was that strange central term in the thing. But for now, feel free to forget about that and just imagine that we have a game and we have a couple of operators, interesting ones, and we declare them to be primary if they fit into this, and we say that the CFT has a central charge C if it fits into this thing. Note, by the way, that these 2 things imply that the stress energy tensor is not primary unless this term vanishes and C is 0. Okay, otherwise, and in that case, the conformal weight of it is 2. Okay, to fit. So if this thing is not there and I compare them, that 2 here is the same 2 as the one here, to make things more mysterious. Okay, so is everyone happy about this kind of statements? Okay. Now then let me introduce the final piece of notation, which is called contraction. So before we briefly seen the Weeks theorem, right? There was maybe during Edward's course, there was Weeks theorem?
Yes.
Yeah, so there will be a Weeks theorem in here, maybe viewed from a different angle. But there is another notation that people use, and they say that if you ever see a symbol like this is what's called a contraction. And by this, I mean the singular part of the OPE. Okay, so I just extract the singular part of the OPE. And most interestingly, there is a thing called the normal ordering. There's many normal orderings in CFTs or quantum field theories. This one is a special one. I think maybe people call it conformal normal ordering. Maybe doesn't matter. It's a way to produce a new operator if you take 2 operators. And you can create a new operator, which is perhaps somewhat confusingly denoted by putting parentheses around this product. So there is a new operator, which is defined to be the fact that you look at the OP and you simply take the term which stands at the absolute power. So this is simply the O alpha 0. So to make it look less
Alpha 0, but it's n from 1 to n. We don't have an alpha 0.
I know it's not part of the contraction, yeah, but it's part of the
Okay.
it's part of the full sum. Yeah, yeah. Yeah, thank you. That's a good point. It's precisely the thing that's not visible by the contraction. But you can write it in terms of the contraction as follows. Well, using the contraction, you can say that this maybe illuminates the origin a little bit better. It's okay. Did I mess up this? Okay. It's precisely the thing you get when you multiply these operators together, and then you try to approach one with another. But this won't work in general because this limit has a pole. So you simply subtract the contraction, which is the singular part. Okay, it's kind of a silly rewriting, but I'm just saying that you just subtract the singular part and then you send the limit, one of the points to the other. I hope I didn't mess the W and Z. There is yet a different rewriting you can write to pretend that you are working more with complex analysis. And that is, you can say that you can use a contour integral. This was contour integral over a small circle surrounding the point Z. W minus Z, O1 W, O2 Z. Okay, so you simply take the product and then you extract the absolute coefficient, which you can do using the contour integration by dividing and then taking the integral. Okay. And then we move on to theorem. Mixed theorem. So there is a handy thing that someone derived before. What happens if you have product, if you make a contraction between an operator and a normal ordered product. If it helps you focus, then I think we will also finish earlier today. After this theorem, I just want to discuss one example and then maybe take some questions, and then we are done. So, okay. The theorem says that you can write this contraction by contracting O1 separately with O2 and O3. And to write it properly in this language, then you need to resort to things like these. Okay, something like this. Point is that you can contract them individually with O2, with one with 2 and one with 3. And okay, now comes the final example. Actually, the only example of CFT that we will see, which is the free boson. The other examples are discussed in the lecture notes, and they are actually similarly simple. So any questions before I start doing this?
Should there be an x in the denominator inside the integral?
That would make sense, yes. But I don't have it here. Let's see. Yes, let's suppose there is x here. Thank you. I don't have it in here, which is a typo, but I have it below in the calculation, which probably means that it's there. Okay, so now to specify this theory, essentially the thing I will do in the spirit of what we discussed here is that I will tell you what the operators are. And so you might remember we discussed these three bosons before a little bit. It was this, there was some action function null in the classical setup. There was a classical field theory behind it. So in fact, what will happen here is that there is one operator O coming by quantizing the theory, which will turn out to be primary, and that's the partial x. So remember again, we are doing just chiral. Everything is there is only z. There is no z bar in this part of the story. You would need to tensor this with some anti-holomorphic stuff. So everything here is just depending on z. It's just like analysis on a Riemann surface or something. There's only one derivative, and I take that derivative of this is a function. But whatever, you don't even need to know. We can just work with O, but instead I will just write del x to make connection with the classical field theory. So this comes from classical field theory, which looked like in complex coordinates. I think it was like this: d2z, dz bar. Well, I think it was something like this. This was the origin of it, for those that are interested. But at the moment, we only have this one operator. And the thing I'm going to declare, this is a result of a calculation really, if you quantize the theory, but I will just start from there. So this thing has an OPE with itself. The singular part looks like z minus w squared in inverse. And this comes, if you know how to quantize things, and this kind of comes by studying the propagator here when you quantize this. The other thing I will assume is that the energy momentum tensor comes from quantization of the stress energy tensor in the classical sense, which was, if you do the calculation correctly, it's this thing. But in the quantum sense, you need to regularize, which is precisely what the normal ordering is for. It's to subtract the bad stuff. So actually, there is normal ordering. Okay. So this is my other assumption. And I will just use these two things and try to see if this works. And it turns out it doesn't, but I need to put some number here. Okay, so this is a number. Real. And the last thing I want to do is that I will just start from this, which again is something that could be extracted from the classical theory if you like. And I will see whether I can make it work, whether I can make del x into a primary operator, and whether I can make t satisfying this thing. And that turns out to first of all fix this number, and it's also going to tell us what c is. Okay, so this is the last game that we are going to play in maybe like 5 minutes. Okay, so the goal, well, for us now at least, is to determine this coefficient by requiring that this partial x is actually primary. Okay, so but before we go into that, let's calculate something. So let's calculate this thing. Because we only know how to use the Wick theorem, so let us calculate this thing. So what is the operator product expansion of partial x? It's E. Okay? I do this because I want to calculate. I want to use this equation I want to recover something like this. Okay. So first definition, there is a number gamma, and then there is a partial x. Z, and then there is this operator product expansion at W. Here I just I use the definition. Okay, but now, since the contraction, so what I can do is for free I can write the contraction here. Because, and then I have to relax this to tilde. Okay, so you see that the contraction differs from the full expansion precisely by regular terms. So they are actually, I can use this equivalent relation. Okay, so far, just definitions. Now I use the Week's theorem. Okay, let's try to do that. So, fortunately I take, in this case, all three of my operators are the same. So I have just del x, del x, del x, del x, everything is del x. And I have a contraction between del x and del x, which I know what it is. It's this. It's the singular part of the OP. It's this thing. So. Yes. X minus W. And if I contract those two things, I can just write this thing, except the arguments were Z and W, and here there are Z and X. So it should be Z and X. Times O3, so times partial X and W. That's the first term. And the second term, I'm fusing and contracting these two things together. So I again use the same thing. Now Z and W, Z and W. So even it works. And I'm multiplying by partial X minus. Okay, so already this is looking good. We have some operator, which is x, but it only enters linearly here, so it's multiplied by some functions, and we want to integrate it. Now, you see that, okay, so now I want to use the formula that if I have a holomorphic function, this f is holomorphic, then if I calculate this thing, and this is f of w. So if I have a holomorphic function, well, this thing I already used before, so, well, okay. And if a function is holomorphic, then by writing this integral, I extract its value with when w. And I want to use that here. So let's see. So what do I get there? So, well, first term only has x of w. That doesn't depend on x. So essentially the function I'm integrating is this one. Now this function here, this is holomorphic in x around w, right? It only has singularity when x hits z. But as long as I stay next to w, then I'm fine. I mean, of course, I'm supposing that z and w are different. Okay. So essentially I can just substitute the value here for the first term. So I get like del x w, and this integral, just using this formula, I can just substitute the value, and I get minus 1 over z minus w squared. That's for the first term. Now for the other term, okay, that's the first term. For the other term, now this thing is independent of the integration variable, so I can take it out. So I only had like this divided by this times some operator, and okay, and this operator, it's an operator. It's complicated, but at least at the point w, it's simply it makes sense to talk about its value. So this is actually like regular, like holomorphic, if you want in w. So I can just evaluate it as well. Evaluating it, I get minus this thing. This thing just went out. And I can just evaluate it, so I get partial x of w. twice. Use this thing twice. Let's see. Okay, so the total result is that I get minus 2 z minus w squared times partial x of w. Okay, that's great. Does it look like this?
No.
No, it doesn't. Okay. Now, it might be a bit too late, but does anyone know? Does anyone see why?
Usually we are applying them in the opposite order.
Exactly. So for this equation, t needs to be first, and here t is second, which seems to be a minor difference. But let's see. No, I need this is the only one I need. Okay, this one I don't. So the only thing we have to do is we have to invert the order. So that's strange. I mean, how can that help us? I mean, we're just inverting things. The operators commute. So. Okay. So what is it that we actually want? We want to have this. We want to have t at z times O, which is our direct, at W. So they commute, so I can just say this is the same as del xw tz. And now I can use the thing that we calculated, except I have to switch x and z, right? Sorry, w and z. So this is minus 2 w minus z squared times partial x of z. And now you see that, well, there is still something to do because I want these things to be expanded at the argument of the second guy, so w. So how do I expand something like this at w, around w? So, well, using Taylor. So the only trick that there is. So it's this plus the next term will be given by the derivative. Times, wait, how does Taylor work? Z minus W, right? I have the value, then I have derivative of the thing at that point, and this plus something else that will contain z minus w squared, etc. Okay, now these things that contain z minus w squared, etc., when they come in here, they will kill this thing and they will become regular. So actually, sorry, they're supposed to be sticking. So actually, up to regular terms, we can ignore them and we only care about the first two. So the result, final result is that we have this one. Here I can solve them because it's a square. And here I will get partial x w, and then I will have minus 2 partial x at w, and one power is killed. And this now has more hope of looking like this. So, is there any chance of picking? Wait, did I mess something up? There was a gamma somewhere, right? There was a gamma there the whole time. Gamma, right? There was a gamma here. Okay, gamma minus 2 gamma, minus 2 gamma, 2 gamma, 2 gamma. Okay. So is there any value of gamma for which I can fit this formula with this one?
Minus a half.
Minus a half. So the second term should be just partial of my operator, and that I can only achieve if gamma is minus 1/2. In that case, then I will have, and this is same happens here, partial x of w so we see that if I choose this normalization here for a stress energy tensor correctly, namely I choose it to be minus 1/2, then actually x becomes a primary operator. What is the weight of this primary operator? 1. Because that's the coefficient of this highest order pole. X, weight 1. And okay, so the only thing that remains to do, but I won't do it. I suppose everyone wants to go to dinner. Is that we can just use the same calculation and just calculate the stress energy, the operator product expansion of stress energy tensor itself. Now this thing contains normal ordering twice, but we already can use the fact that we know what this is. So to use the Wick theorem, and so you can calculate, kick it a little bit, and then you will end up precisely. You need to fix the normalization, of course, to be minus 1/2 that we determined. This is our normalization. But once you do that, then you end up precisely with this description, and the C will turn out to have value 1. Blah, 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 and this thing will have C equal to 1. Okay. And so, if for whatever reason you are keen on playing these kind of games, then you find more material in the lecture notes. So there is a bunch of other things which start similarly, like there is, for instance, a free fermion, which essentially starts by saying the same things, but you start with a different OPE in here, again, which is extracted if you want. Someone extracted using quantizing the theory and looking at it, but you can just take it as a result and you can try to check whether it works, and it works. And it will have some different value. For instance, the central charge will turn out to be 1/2 for the theory. There is also a fun story where you keep the first OPE, but you modify the second one. You define the stress energy tensor to be something different in a precise way. This is called the linear dilaton CFT. So you can have stuff like that. So you have the same OPE of the field itself, but you modify the stress energy tensor. Just physically, it means that you define your symmetry to be something, not the immediate thing, but something different. And then then there is also an example where you can recover the WCW model, the Wesumin-Witten model, where you start by postulating again something of this form, slightly more complicated, and then you end up with a nice formula for the central charge, which uses some Lie algebraic data for a given Lie algebra. So if you're interested, you're welcome to have a look there. But apart from that, I would probably end it here. So maybe take some questions.
So this is a free model. What happens when you include interactions in the model? Is there something that changes?
If you just randomly add interactions, like the quartic scalar field theory, for instance, that won't be conformal.
Oh yeah, true. You have to make sure interactions are conformal.
Yeah, but the famous generalization of this, which will remain conformal, is the one of this the Polyakov action, the one for string theory that we had when you study maps between two things. That one, it turns out that if you quantize it, it will stay conformal, but if and only if the metric was Ricci flat. And there is a generalization of this where you also add other fields from string theory, and then you have some generalization of Ricci flatness, and then you can go even more complicated and all that. So these are string vacua, those CFTs. They correspond to string vacua. So kind of the basic configurations of stuff, of the physical system, which are satisfying kind of sort of basic solutions to the equations of motion of the theory, and then when you quantize, you study expansions around, fluctuations around that thing. It doesn't matter, but catchword is that, or keyword is that CFTs, central charge 26 or something, something specific, they correspond to string vacua. Sorry?
42.
In this case, it's 26 or 15. I think it's 26 probably.
Thank you. I also have a second question. So this was the whole story in 2D. what happens when you go to like more dimensions? I mean, you said at the beginning that the algebra or like group becomes finite dimensional. So is the theory still enough constraint to be able to do nice things, or?
It's kind of halfway. My understanding is that it's still very nice in that you can recover the correlators from just like a much smaller amount of data. That's what I understood. But it's not nearly as well constrained as here. So here you can do some like analytic things, like determine things exactly, and in higher dimensions people typically just do some simulation, some like bootstrap. They can still use like bootstrap to kind of determine the values, but it's like numerics. They can't like pinpoint a point, but it's more like, right? Well, okay, I think it's less constrained, but it still retains some of the nice structures. I think especially in recent years, people have like studied higher dimensional models. Like there have been some breakthroughs in like trying to do these things. Like I think 3-dimensional Ising model is maybe like yeah. Yeah. So yeah, if you study ADS-CFT correspondence or holography in string theory, then typically what you have to work with higher dimensional CFTs. That's, for instance, very superior. Yeah. So funnily enough, the group is finite dimensional, but still it seems to constrain the theory somehow a lot. This is my understanding. Precisely because apparently it doesn't matter that it's not as important that it's finite dimensional. It's more like that it's tied up with the scaling of the systems. So you can kind of study like some correlators by kind of imagining that it actually doesn't matter if you put them closer or not, and then you can expand if they're very close and stuff like this. It's like a special nature of this symmetry. Maybe matters more than the fact that it's finite dimensional. But it matters a little bit because 2D is still better than like more constrained. Any other questions? Yes.
So there's another question. So far, we've only focused on the space-time symmetry. That is, we want conformal symmetry on space-time. What happens if we also include internal symmetries in the system? So on the level of the fields.
I don't have anything deep to say about that, except that like I guess this is what happens in these higher dimensional CFTs. Like there you have like other things. Like there could be like an SUN group in like n equals superioung for instance. So there is just like further structure, I would say. But it's probably the same as in like QFT, that you have like internal symmetries and you have like Minkowski or like Poincare symmetry, and they kind of don't talk to each other that much. It's more like.
So essentially the Mandela theorem holds.
Well, yeah, I think that's what I was going for. I'm not sure I can prove this, but those things don't mix. Well, on the other hand, you have these WCW models, and there is much. You replace Virasoro by something that involves a group, and they mix very much. So maybe I retract my statement. But if you just tensor the thing with something, then of course, by construction, it doesn't interact. So I guess it really depends on what precisely you mean by internal symmetries, maybe. So it could or it doesn't have to make go, I would say.
Okay, so there could be interesting behavior if that's what you're studying.
Yeah, like the WCW theories have very interesting behavior. They are kind of like maybe sort of of this type. Okay, and if not, you can also ask me at the dinner later. So thank you very much.